Somebody cuss it one more time in here. I'm gonna stop. Is it you, Matthew? Are you potty mouth? Yes, like got 3 foul words. Because Mr. K was talking. Yes. Dirty language. All right, here we go. So last night, you guys, we kind of began this process of estimating area underneath of a curve. So there are 3 big ideas in calculus, okay? The first one, the most fundamental one, is limits. We haven't talked about them yet. Limits are the heart of everything else. You don't know why, you haven't gotten there, but limits are the foundation of calculus, okay? Limits are what give us the other 2 big ideas, derivatives and integrals. And we just talked about derivatives. All those little rules you came from, that we learned last time, you're going to see where they came from. They come from doing limits on a slope, and we'll show you where they come from later. Once again, here we're going to talk about the next big idea in calculus, which is integrals. Now, the reason I'm choosing to talk about integrals right now is because we're going to do the same thing this chapter that we did last chapter. Last chapter, all I did was I gave you rules so you can memorize them and start using them, because they're like the most important tools you can have in the class. So I want to start you having them early and using them early so you can practice them. Same thing with integrals. Integrals, I'm just going to give you the rules. You're not going to know why they work, but you're just going to have them. Now, what integrals are is they are the opposite of derivatives. So on part 2 of your homework, I asked you guys to find the original function. So down here we had f prime of x. So if f prime of x was 2x, then what did you say was your answer for the original function? X squared. You're right. Don't you guys agree if you took the derivative of that, you get 2x? Now, let me got an itch on my foot, sorry. Okay, now, don't you guys agree, though, that there could have been a number here? Yeah. There could have been, but we don't know. Okay? So, something you probably don't have is you could just put plus c. It means there could have been some random constant there that just disappeared after we did the derivative. Okay? But you have the idea. You have the idea. That's good. All right, let's go ahead and take a look at the next one. Chloe, what did you put for number 2? X cubed is correct. Once again, there could have been some random number there, right? But the derivative of that would be 3x squared, right? Let's do another one. Neha, what'd you get for number 3 down there? It's starting to get a little bit harder. Are you just making this up like right now? You didn't do your homework? You're a bad person, Neha. You're a bad person. Let me see. Hold on. And judged. Okay. So you said what? You're lucky you're a smarty pants. That's right. If you took the derivative of this, you would get 6x squared, right? But there could have been some random number there that we didn't know about. All right, last one, number 4. Vivian, what'd you get for number 4? Oh, no, it's not the last one. What'd you get for the last one, or number 4 there, Viv?
4.
Yeah. If the derivative is 4, then it was 4x. And once again, there could have been some random number after that, right? Lastly, we have John B. John B., if we took the derivative of a function and we got f prime of x equals 0, what'd you get? 2. Sure. So long as it's just a number, right? Or we could just put c, right? Any random number would have been fine, because the derivative of that is 0 means that it was a constant function to begin with. All right. So what you guys just did is what we're doing today. Now I'm going to give you harder problems than this, but you guys actually already know how to do it intuitively. And you did the opposite of a derivative, and that's called an integral. And that's what we're learning this whole chapter. So you're going to find that it's easy in the sense that Well, we're doing the same thing we did last chapter, where it's working backwards most of the time. The bad news is what you learned last chapter is going to get mixed up with what you're learning this chapter, and you're going to have to keep them separated. So this is where those flashcards are going to come in pretty handy. Like, here's the worst one that kids struggle with. What's the derivative of cosine? Negative sine. So if somebody did a derivative and they got cosine, then what was the original problem? Sine. And you're not alone, Matthew. That's the one people struggle with a lot. So you'll see when we get there. But it's just that negative that messes people up. So the rules from derivatives are going to get mixed up with the rules from integrals, and that's going to be your biggest enemy in this chapter. But it's going to be easy in the sense that you kind of already know the rules, just working backwards. But the problem is keeping them separated in your brain. Okay? So there's that. But now you guys remember we talked about derivatives, but derivatives meant something. What did derivatives mean? They were slopes, right? They were slopes, instantaneous rates of change, instantaneous slopes on a curve, right? Well, integrals mean something too, and it's not at all obvious. It's really weird. But integrals actually tell you the area underneath of a curve. Isn't that weird? You're going to see that come out a little bit. But basically, if I told you guys that this line here is f, if we take the integral of f and plug some numbers in, I won't tell you what numbers we're plugging in yet, but if you take the integral, you find the opposite of the derivative, right? We call it the antiderivative. You can call it integral. If you find the integral of f, working backwards from derivatives, plug some numbers into that, you can actually find the area underneath of the curve, okay? Now, just to kind of prime your brains for the activity, I gave you this, right? You can estimate the area underneath of a curve using rectangles, right? If your rectangles go above the curve, then you're getting an overestimate. If they go under the curve, you're getting an underestimate, right? So if you know this answer and this answer, maybe you can just average them and get really close, right? Still won't be exactly right, but you'll get close. You guys good? All right. Or here's another way to get a better answer. Make more rectangles. The more rectangles you have, the less error you have, and therefore your estimate gets closer. And this is where limits come into play. This is where integrals actually are limits. So you remember what a limit is. If you don't, I'll remind you right now. A limit is where you are approaching something, getting closer and closer. If you take these rectangles and you let those rectangles get smaller and smaller and smaller into infinity, eventually that error between the rectangles and the curve is going to become 0. And you'll actually get the exact area under the curve. So the way that you can actually find integrals is by setting up a formula that represents all these rectangles being added together. Find the limit of it as the rectangles approach an infinitely small width, and whoop, pops out of it a formula that gives you the exact area under the curve. And it just so happens that that formula is the same thing as taking the opposite of a derivative, which is really weird, but it just so happens to work. Crazy stuff. Good stuff, but crazy. All right, so that's it. So go ahead and pass your homework forward. We're going to move on. We're going to do some integrals today. By the end of the day, you guys should be able to tell me what an integral is. Now you should already be able to do that. Somebody want to earn an extra point right now? What is an integral? Yes, Jimmy?
It's the area underneath the curve.
Beautiful. Can somebody give me another definition? Because that's true, but I want more. Yes? Beautiful. You guys are like, I love having great students. That's it. So it's the opposite of a derivative, and it tells us the area under a curve. That's beautiful. You guys got it. I'm so happy. It's blessed me.
I switched notebook. I used this notebook. I switched to this.
Oh. You can for now. I'll talk to you about it in a second, but for now, just don't put it down. All right. So then I'm going to teach you guys about the notation. Just like derivatives have notation, we're going to talk about integral notation. Next, we're going to actually do some problems. Okay, just like you did on your homework last night, but I'll try to make them a little bit harder. All right, here you go. So you already know it. What is integration? It's the opposite of differentiation. I printed this for you, right? So if x squared plus 5 equals 2x, we call that differentiation, right? If x squared plus 5, the derivative of that is 2x. Integration is where you have 2x, you integrate it, and you x squared plus something. You don't know what that something is. It got lost in the process. Okay? Here's our notation. Okay. Before I start talking about this crazy looking mess, I want to remind you guys of derivatives, right? So if you have f of x, we had notation for that, right? The derivative could be like this. Right? It could be this. I don't know, let's put f. Or it could be this, right? Integrals don't really have a whole lot of ways. This is pretty much the way you show an integral. So that's good. You have less to memorize there, but they look a lot uglier. So, but just remember that subtle thing about derivatives? This thing actually kind of mattered down here. You remember that? That was the one that you were finding the derivative with respect to. Remember implicit functions? If they didn't match, that meant you got a y prime. Or if it wasn't even a function of it, it was like a constant, it just went away. Same thing applies to integrals. You can, just like you can differentiate with respect to x, you also integrate with respect to a certain variable. You're applying the integral to only a certain variable. So let's take a look at our integral notation. First of all, this is the integral notation. Now that's not random, I've been told. I've been told that this is meant to look like an S. And it's meant to look like an S because S stands for sum. And sum means what? Add things up. Did you guys add things up on your homework last night? What'd you add up? The rectangles, because it tells you the area under the curve. So what this means is we're adding up all the rectangles under the curve of f. Okay, so that's your symbol for an integral. And right here, there's your dx again, right? It makes another appearance. Yep. And that tells you which variable you're integrating with respect to. Okay, that tells you the variable that you're integrating with respect to. Now, what do you guys notice about the difference between this f of x and this f of x? One's lowercase, one's capital. It's a subtle difference, but it actually matters. Okay? The lowercase means that's the original function known as the integrand. After you integrate it, you get a new function, right? Like on your homework, you guys had 2x, and then I think it was, they had told me it was x squared, right? This would be your f, the original function. After you integrate it, right? There's my integral symbol with respect to x. What I get out of that is the big F, a new function. Okay? That new function is called the antiderivative. Makes sense, right? The opposite of a derivative. Good. So there's that. And then you always get this guy. Remember that plus C I kept throwing in all my answers up there? Because when you integrate, there always could have been some random number that disappeared in the process of the differential, the derivative. So there we have our constant integration. So there's all your parts. So I'll say it all again. This is your integral symbol. It means we're adding because we're adding up together an infinite number of miniature rectangles. Second, that's our function. That's our function that we're finding the area under the curve for. That tells us what variable we're doing with respect to. The outcome has a capital, and it's known as the antiderivative. There's always a ghost, C, hanging out there. It's known as the constant of integration. Here we call this the variable of integration. So that way you know which variable you're integrating with respect to. Okay? So that's your integral notation. And so I could have written your homework now differently. Instead of giving this long-winded thing like, okay, Zarina was doing a problem and she got f prime of x equals 2x. What was her original problem? I could have just given you guys this then. And that means the same thing. You good? All right, so, oh, there it is again. Well, let's do it. I wonder what it is. As you guys can see, I'm really creative. I've got so many ideas in my head. Got all these different examples. They're all different and unique. All right. Did I print that one for you? No. Okay, you don't have to write it. It's okay. You guys, I think you guys have the idea. You good?
I think you should go over it.
Go over it.
Go over it.
I can't. Stop. All right. The reversal of the power rule. Now, you guys know this intuitively, but now I'm going to give you a formula, and you're going to all of a sudden not understand. You got it on the homework, but as soon as I turn it into a formula, you're going to be like, but you did it. So don't let my formula scare you. It's exactly what you did in your brain. You just don't believe me. Okay? So you guys remember the derivative, right? If this is my original function, what do we do if I want to take the derivative? I put the n in the front, right? And we take 1 away from that. You guys good? That's the formula. Okay? What if we're working backwards? What if I want to take f and integrate it? Well, first of all, instead of multiplying by n, what do I want to do? You're going to divide, right? And instead of subtracting 1, you're going to want to add. So here's your process. The first thing you're going to do is you're going to take your power and you're going to add 1 to it. You good? And whatever you get for that, you're going to divide by that number. Okay? And that's exactly what you did on your homework. You just don't believe me yet, but you'll see. It is the same. So that's your formula. So, and I would label these steps. I would say step 1 is to add 1 to your power. Step 2 is to divide by that answer. Okay? Over here it was different though, right? Over here we multiplied first, that was step 1, and then we subtracted 1, that was step 2. But since we're working backwards, right, we start here and we add 1, which makes it n instead of n minus 1, right? And then we divide it out, right? Working backwards. Okay. So, do you guys remember the constant multiple rule? If you take the derivative of a function that's being multiplied by a number, do you remember that number doesn't really matter, just stays there? Okay? Same thing applies to integrals. If you're taking the integral of a function and there's a number there, just take it out. It doesn't change anything. It just comes out. But I said, what is this thing? It's a what? What did I call this? It wasn't, okay, good. A number or a constant, right? Can you do that with an x? No, because the x is being integrated. The x matters. If you take that out, you screwed it up. But numbers, that's not an x. You can take the number right out. That's not going to change. Okay? All right, so constant multiple rule. So just like the integral of 2, like let's say the derivative of 2x, right, squared would be 2 times 2x. You guys agree? Put the power in the front. That 2 just kind of stays there. It doesn't really do anything. Same thing with integrals. If you are taking the integral of 2x, that number, before you apply the rule, you can just kind of take it out of there. It doesn't need to be part of the process. Okay? You'll see when we get there. But my point on this slide is to show you that all the rules we have for derivatives are going to apply to integrals too. Like here's another one. When we took the derivative of 2 functions that were being added and subtracted, didn't you just take the derivative of each one separately? Right? Remember that? So like if I had x squared plus 3x, it was 2x plus 3, right? Take the derivative of each one separately. Same thing applies to integrals. If you're taking the integral of 2 functions that are being added together, then just apply the rule to each one separately. Okay? You had a question, Andrew? Sure. All right. So we're going to do some problems now. Now we're getting down to business. So go ahead and write down number 1. Or did I print it for you? Okay, go ahead and write down number 1. Now I could probably have you guys do number 1 on your own and you would get the answer. So why don't you? See if you can get the answer, just like you did on your homework. No formulas, just think about it. Try to get the answer. Okay, so for those of you guys a little bit confused, what that means is that I'm going to call this f prime. My question is, what was f? So if this is the derivative, what was the original function? Does that make more sense? It's the same question, it's just written differently. So see if you guys can figure out what the original was. You got it, Chris? What'd you get? 4x cubed is correct. 4x cubed is correct. Plus c, good, right? All right, but yeah, 4x cubed is the difficult part. So now, even though you guys just did that mentally, I'm going to show you how to use the formula because that's going to help us on the rest of them. Ready? So let's go back to this. So first of all, you guys have got to know the math language, right? And so I could tell by when I posed the question, you guys still weren't quite familiar with it. This really means, I want you guys to think of it this way, that means, okay, my derivative is 12x squared. What is f? That's what that means, okay? But now that you guys know what that means, let's go ahead and do it. So instead of doing this intuitively and just kind of reasoning our way to the answer, let's apply the formula I shared with you guys. So here's the formula I shared with you guys. Ready? The formula I shared with you guys was step 1 is to add 1 to your power. What would that give me for my power? 3. The next step was to take that new number and divide by that number, which would be what? That's right, 4x cubed. And we don't want to forget our plus c. So there's our final answer. So your two-step process, add 1 to the power, and then whatever you get, divide that into your problem. Good? All right. So before we go on to a harder one, I want to throw one more at you. And I'm going to have you guys walk me through the process. Ready? So 5x to the third. Write it down. Let's go ahead and write that down. That's not, I didn't have that on the slide, so we'll write it down. Freaking Julia. Are you serious? That child. All right. Julia, I hope you're watching this. You're being judged. All right. Savannah. Savannah, what's the first thing that we do? Add 1 to the power. So what would I get there, Savannah? Good. That's step 1. Step 2, Tricia? After we add 1 to the power, what do? We divide by that number, which is 4. And we may be tempted to, but you won't after a while, Angelina. You don't want to forget to do the what? I see. You've been paying attention. That's good. Thank you, Tara. All right, so that's the reverse power rule. Okay? So let's do another one. Go ahead and write down 2. Hey. The one that I did previously, I don't need to what? Yeah, so the one that I just did couldn't be simplified, right? The first one I did, I had 12 over 3. I simplified that one to 4 because I could. So if you can simplify, do. But the one I just had could not have been simplified. All right. So let's go ahead and take a look at 2. Okay. So here we go. Just like derivatives, we're not going to leave it written like this, are we? we're going to change it first. It's going to be negative 8x to the negative 5. So the first thing you're going to want to do is rewrite it. Okay? Now we can apply our reverse power rule to it. Okay? So if step 1 is to add 1 to the power, what would that be? That would be negative 4. And then step 2 is to divide by negative 4. Don't forget your plus c, right? What's negative 8 divided by negative 4? 2. We can leave our answer like this, but hopefully by now you guys know how you can also write that answer, right? So there we go. So that's our final answer there. Let's go ahead and do another one, number 3. We're going to start by rewriting this once again. Negative 5, and it's going to be x to the power of 2/3. Right? Okay, now we got used to these fraction ones with powers, right? You guys remember when we did we had the fractions, what we did was we did we subtracted the bottom number from the top. So if we subtracted 1 from this, we would get negative 1/3. You guys good? Okay, well now we're adding. So instead of subtracting the bottom number from the top, we're going to add the number on top. So check this out. Ready? Here you go. We'll practice one like this in a second. So step 1, we want to add 1 to that. So what that's going to be is I'm going to add 3 to 2. What's that going to give me? 5, but keep the bottom number, right? So it's going to become 5/3. But we also need to divide by 5/3. Don't forget your plus c. Now your answer is not going to be left like that. So right now I have this, right? You guys good? Okay, now you guys know the rule about dividing fractions. When you divide fractions, what do? Keep, change, flip. Remember that? So I'm dividing 5, so keep. I'm going to change it from division into multiplication, and I'm going to flip. Okay, now in the future, I'm not even going to show this step anymore. We're just going to basically go straight from here to here. Okay, so when you divide by a fraction, that's the same thing as multiplying by the reciprocal. You guys good? And so here the 5's go away, and I'm left with negative 3x to the 5/3 plus c. So I'll do another one with these, and I'll let you guys practice one of these ones, because these ones are kind of crazy. Un poquito loco. You guys bueno? Ready? All right, let's do another one. Let's see. I want to do 6x to the of the 3rd root. No, let's do the 4th root of 3. There you go. Okay, step 1, I want you guys to rewrite it. So I'm going to call on someone to share with me what goes there. I just want to rewrite it first of all. We're not doing any calculus yet. We're just rewriting it. I'm going to ask Schofield. Aquí? Bueno. Okay, now the next thing we're going to do is I want you guys to add 1 to the power. Add 1 to the power. What do you think, Mr. Graydon? You got it yet? Yeah, if I added 1 to 3/4, what would I get? Very good. Okay, now the next step I'm going to be weird. Because the next step is I'm supposed to divide by 7/4. But I told you I don't want to do that anymore. Because when we divide by a fraction, ultimately we're just going to multiply by the reciprocal. So I'm going to ask Mateo, what do I put times of? Huh? 4 over 7 is right. Okay, we're not going to do the divided, but you can if you want. I just think it's a waste of time. So we're just going to do times 4, 7. Don't forget your plus c. And we do want to simplify this, so what would that be? 24 over 7, x to the 7/4 plus c. Bueno? So with these ones, just remember the one difference is really just that instead of dividing by the outcome, we're going to multiply by the reciprocal, which is really the same thing, but it's just more helpful when you're talking about fractions. So let me throw one at you. Let's have you guys do 3/5 root of x squared. You guys do that whole thing from beginning to end. Find me the final. So we would rewrite it first. We would add 1 to the power to take the integral. That would be 7/5, because 5 plus 2 is 7 over 5. And then we have our 3 here. But we're also, instead of dividing by the power, which is what the rule usually tells us, we're going to multiply by the reciprocal since it's a fraction. And so don't forget your plus c, but our final answer will be 15 over 7 x to the 7/5 plus c. Okay, so there's that. All right. Let's do another one. We have a few here. All right. I don't need to rewrite anything here. I don't need to rewrite anything because there's no square roots and I don't have my x in the bottom, so we're good. We can just begin. So what would the new power be? 7/3 is correct. 4 plus 3 is 7 over 3, right? Don't forget your over 3 here. Now, is my power a fraction again?
No.
Is my power a fraction? So we're not going to divide by the fraction. Instead, we're going to multiply by its reciprocal, right? The 3's cancel. 7 goes into 14 twice. And we have 2x to the 7/3 plus c. Bueno? Next one. So now the next two examples are mostly review, but with one new concept added. We have a bunch of parts. But we learned that since integrals are the opposites of derivatives, a lot of the same properties of derivatives apply to these. So just like if you're taking the derivative of something with a bunch of parts, you just take the derivative of each part separately. Well then, when you're taking the integral of something with a bunch of parts, you just apply the integral to each part separately. So, you guys ready? Let's do it. All right, so for this one, we're going to take the integral of this first. I'm going to add 1 to the power, which would be, did you guys write it down yet? So we have x to the 6th, and I'm going to divide by 6. Plus, I'm going to add 1 to the power, and I'm going to divide by 4. Okay, here's an interesting one we haven't done yet. What's that going to be? That's derivatives. 3x. You get an x, okay? Plus c. You might want to put a star next to this one on your notes because I could show you the reverse power rule actually applies to this, but it's awkward and unnecessary. So just remember, if it's just a number, just put an x next to it. Just like when we had derivatives, if it was 3x, just drop the x, right? Yeah. Well, after you take the integral, you don't need the parentheses anymore. So, but we can simplify this, right? That is negative 4x to the 6th plus 5x to the 4th plus 3x plus c. So as you guys can see, you're just taking the integral of each piece separately. Huh? That's it? That's it? You like? Do you like what you see? Okay. All right, go ahead and write down number 6 if you haven't done so yet. Last one I'm going to show you before I set you loose in some student practice problems, and that just might close us out for the day. We'll see. Okay. Can I delete? That's interesting. It's green. No. I don't like that. There we go. Okay. So let's begin. The first thing I'm going to do is I'm going to rewrite it. This guy's fine, right? This other guy here, I don't like how it's written. I'm going to change it to 15 over 4 x to the 1/4, right? We don't like square root. I also want to rewrite that one over there on the end as 3 times x to the negative 4. Well, I haven't done the integral yet, so there's no plus c yet. All right, so now that I've rewritten it, now we go with our power rule. Add 1, divide by 5. What's it going to be? There we go. Next one. Add 1, multiply by the reciprocal. Last, add 1, divide by negative 3. What do we get? Plus 1, right? It becomes 1 because the negatives cancel. Don't forget the c. And there's our antiderivative. Yeah. Yeah. Okay, so that's it. Go ahead. These are for you. Okay, there you go. Reverse power rule, areas under curves, opposites of derivatives. Good stuff.